we can listen to Siska today talking about dark matter.
All right. Thank you so much for having me. I'm so sorry that I couldn't make it there. Yeah, the Dutch railways were not wanting me to get to Utrecht, I guess, or the snow, who knows. But anyway, I'm really happy that I was able to like do this online at least. So good. Perhaps to very little surprise, I'm going to talk about dark matter, especially if you've seen me talk at the conference in Utrecht a couple of months ago. And because I'm going to talk about dark matter, it means I have to update my title slightly, which I guess is also reflective of the part that I am nowhere near organized enough to be able to give a definitive title for a talk more than 3 months in advance. So I'm sorry about that. Anyway, so the background for this talk and for a lot of my work is the dark matter problem. And I know this will be quite repetitive for most of you, but I am going to start with some general introduction just for the purpose of making sure we're all on the same page. So dark matter itself has, over the last couple of decades, taken central stage in physics, and rightfully so, right? It's part of the concordance model of cosmology, lambda CDM, which you see here with this funnel. Lambda CDM describes the evolution of the universe over 13.8 billion years, and at the largest scale, the model is highly successful in modeling structure formation and recovering current observations. But of course, the success of lambda CDM depends on it positing the existence of lambda, dark energy, cosmological constant, but also, more importantly for the current talk, cold dark matter. And cold dark matter is responsible for approximately 27% of the current energy density of the universe. This energy density budget changes over time, but it is the case that there is about 5 times as much dark matter as there is baryonic matter. Importantly, dark matter is distinct from baryonic matter, matter which has a non-zero baryon number, which is most of the stable matter described by the standard model of particle physics. And it doesn't interact electromagnetically, hence the moniker dark. But the presence of dark matter in the universe, as well as its abundance, is broadly supported by various kinds of evidence in the universe. But at the same time, there are several open problems about dark matter, and 2 of the most important classes of problems are the following. First, there is the behavior of dark matter on subgalactic scales, or what cosmologists and astrophysicists tend to refer to as smaller scales, right? Because lambda CDM predicts that each galaxy sits in a dark matter halo, and it also predicts some substructure within that halo, like subhalos, which are the result of bottom-up gravitational clustering that is at the basis of structure formation, as well as and you have things like globular clusters, dwarf galaxies, and so on. But when it comes to predicting the shape of the halo, as well as the substructure in the halo, there are some discrepancies between the predictions that are derived from lambda CDM using highly complex computer simulations and the observations that have been made. In a previous paper with Nora Boyd, I've argued that the small-scale challenges don't warrant any kind of abandonment or modification of lambda CDM, but at the same time, Nora and I both recognize that the small-scale challenges do imply that something is not well understood about the behavior of dark matter at subgalactic scales, be it the observational side or the simulation side, the modeling side, right? Now, a second type of question about dark matter focuses on the supposed individual entities that are responsible for the collective behavior of dark matter that is described by cosmology and astrophysics. And this is why dark matter doesn't just take central stage in astrophysics and cosmology, but also in current particle physics. For instance, right, the 2020 update to the European Strategy for Particle Physics lists the quest for dark matter as one of 4 of these other essential scientific activities for particle physics. The fact that they're called other essential scientific activities refers to the fact that these 4 aren't directly related to the building of a new accelerator that would succeed the LHC, basically. So those are sort of like the main 2 families of problems that exist in current scientific research on dark matter. When it comes to the philosophical literature, there are a few papers on the epistemology and methodology of searches for dark matter candidates, so fundamental dark matter candidates. I'm thinking here in particular of recent papers by Rémi Jreg and Antonis Antonio. But The epistemology of cosmological and astrophysical research into dark matter, which is, and especially like the research into the small scale challenges, which is this first set of open problems that I mentioned, is a little less systematically investigated. And so my goal in this talk is to make some headway into proposing a little more of an epistemic framework for astrophysical dark matter research. I should flag here that there has been some work. Melissa Jacquard and Michael Weisberg and collaborators have done some work on the dark galaxy hypothesis, which is this hypothesis that there are certain galaxies that are made entirely out of dark matter, and they're trying to find them, basically. I think this work is highly interesting. I'm not sure all of their claims generalize necessarily. So what I'm going to try to do today is establish 3 claims. First, I'm going to argue that what I'll call astrophysical dark matter research essentially relies on what I call, or so-called, not what I call, so-called local eliminative reasoning. And this idea of local eliminative reasoning is something that I'm drawing from Shannon Abelson's recent paper. I'll secondly try to establish that astrophysical dark matter research tends to be multi-purpose, which implies that astrophysical dark matter research can contribute to progress on more than the dark matter problem alone. And, oh, there was a sound, there was a noise. Did I do something? Everything okay?
Someone joined.
Okay, cool. The third thing I'm going to try and establish is that the success conditions for astrophysical dark matter research are much broader than are usually recognized, though there are some limitations that I'll discuss at the end. So here's how I'm going to proceed for the rest of the talk. First, I'm going to distinguish between 2 dark matter concepts, which is old news for those of you who were at the HPC conference or workshop last summer. So I'll be brief about this distinction. I will show that research into astrophysical dark matter relies on local eliminative reasoning. I'll argue for this multi-purpose nature of astrophysical dark matter, where I'm going to focus on the use of stellar streams. And finally, I'm going to consider some of these important limitations, and then I'll conclude. So let's start with the 2 dark matter concepts. So the first step to the first step is to understanding the epistemology of cosmological and astrophysical dark matter is recognizing that different types of dark matter research are informed by different kinds of dark matter concepts. And these I'll call astrophysical and fundamental dark matter. Let me stress, these names are just labels because you have to label things. I don't mean anything deep by the label fundamental or anything like that, okay? So astrophysical dark matter is a form of non-baryonic matter that behaves as a collisionless fluid. It's slow moving or cold. It doesn't interact electromagnetically. It can only interact minimally through the strong interaction and constitutes 27% of the current energy density of the universe. This is basically the dark matter concept that has been empirically supported by observations like the bullet cluster, galaxy rotation curves, and so on. And that's basically supported by the observations from astrophysics and cosmology. It's a concept that functions in astrophysics and cosmology. Fundamental dark matter is any specification of a constituent of dark matter. So any particle or entity that satisfies the conditions laid out by astrophysical dark matter, and that further specifies some other properties. Now, other philosophers have drawn some distinctions between different dark matter concepts. Niels, for instance, in his paper from 2022 on dark matter realism, distinguishes between a thin and a maximally thick common core concept of dark matter. That more or less maps onto this distinction, though Niels also draws a distinction between a thin and thinnest common core, which I disagree with for separate reasons. Eugene Weinberg describes the dark matter concept as it emerges out of cosmology and astrophysics in a paper in favor of dark matter realism. That's more or less my astrophysical dark matter concept. And so there are some other distinctions that people have introduced. I think there's reasons why mine is slightly different and why I might disagree with some of those other ones, but those are sort of details that I won't go into today. But in case you're wondering, this distinction is also present in the scientific literature. Here's what the particle data group has to say in the opening paragraph of the paper about dark matter. They say modern cosmological models invariably include an electromagnetically close to neutral non-baryonic matter species with negligible velocity from the standpoint of structure formation, generically referred to as cold dark matter. For the benchmark, lambda CDM cosmology, the dark matter accounts for 26.4% of the critical density in the universe, or 84.4% of the total matter density, which is the energy density budget without dark energy. And so this is more or less what I would refer to as astrophysical dark matter. But here's how that paragraph continues. They say that the nature of only a small fraction, between at least 0.5%, given neutrino oscillations, and at most 1.6% from combined cosmological constraints of the non-baryonic matter content of the universe is known, the 3 standard model neutrinos. The fundamental makeup of the large majority of the dark matter is as of yet unknown. And of course, when they say unknown, right, they mean that there is a vast range of possibilities for the fundamental makeup of dark matter, for properties that dark matter could have, but for which no empirical constraints are as of yet available. And so that fundamental makeup is what I refer to as fundamental dark matter. And as another reminder, for those of you who are at the workshop, what is the relation between these two concepts? Here the chart helps, right? The black, purple, and blue all represent possible extensions of the standard model of particle physics. So not the standard model of cosmology, right? Particle physics. Like these are all sort of like so beyond the standard model physics. And some of this beyond the standard model physics could also constitute dark matter, but not all of it can. And so which ones could constitute dark matter is determined by the astrophysical dark matter concept. In other words, the astrophysical dark matter, right, the dark matter concept that we get out of cosmology and astrophysics sets the boundaries for the space of possibilities for fundamental dark matter. And that space of possibilities is highlighted by the red shaded region on the plot. So candidate fundamental dark matter concepts are points or regions within the space of possibilities in the red shaded region. And what this means is that making progress on the dark matter problem can take 2 forms, right? You can either try to positively confirm a region or point in this space of possibilities, or you can try to tighten the constraints by making the red shaded region smaller. And these 2 ways basically correspond to sort of the 2 open problems that exists about dark matter that I talked about in the introduction. And so what I want to focus on is the latter, is on tightening the space of possibilities. Because that kind of research, like trying to tighten the space of possibilities, amounts to enriching the astrophysical dark matter concept. Okay? So that was a recap of these 2 dark matter concepts that I think play a role in scientific practice. So now I'm going to zoom in on research into the astrophysical dark matter. And the way I want to go about this is by looking at one of the most famous lines of evidence for dark matter, which is the bullet cluster. The bullet cluster is this merging event between 2 clusters of galaxies where one looks like it's moving like a bullet through the other, right? And famously, scientists were able to map out where most of the ordinary matter is and compare that with where most of the gravitational mass is. The pink highlights where the baryonic matter is, which is mostly centrally located. This was observed with X-ray observations. Scientists were also then interested in figuring out where most of the gravitational matter is. And they figured that out through gravitational lensing. And what they found out was that the gravitational mass is primarily located in the blue shaded regions. So clearly in a place that doesn't line up with where most of the baryonic matter is. And what's important, right, is that this result is quite robust because it doesn't actually depend on specifically general relativity as a theory of gravity. And so because of its robust nature, the bullet cluster was touted by scientists in the paper title as direct empirical proof for the existence of dark matter. Now, if we look at the discussion section of the bullet cluster, what's interesting is that before they conclude that this bullet cluster really is this direct empirical proof, right? There are, in fact, a lot of alternative explanations that the authors consider for their observations. The first set of observations are, or the first set of explanations are that there are some masses in the line of sight that cause the observed displacement, right? Like some galaxies or other kind of massive structures that are in the line of sight. And they exclude this based on probability estimates for the presence of structures that would have the right lensing strength, but that would not have otherwise been detected, right? Because like they already in their observations try to eliminate foreground galaxies and things like that. So like they're trying, so like the alternative, like if there's a mass in the line of sight, it would have to be some kind of structure that they wouldn't have detected otherwise, but that still has the same, like the required lensing strength to cause the sort of observed displacement of the gravitational mass, or the detected observation of the like distribution of the gravitational mass. And probability estimates based on background knowledge of cosmology and astrophysics basically tells them that that's extremely unlikely. The second possible explanation is kind of similar, where it's about two large filaments that just move right in the line of sight as they were making the observations. And once again, they exclude this based on probability estimates. Finally, they look at alternative theories of gravity, right? Like maybe there are assumptions that go into the gravitational lensing detection or observations rely still on some theories of gravity, and we need to account for alternative theories of gravity. Again, they exclude this explanation, and they exclude this now based on the fact that any alternative theory of gravity would still require the presence of dark matter. But in order to account for the observations of the bullet cluster, the high amount of dark matter that would be, the high concentration of dark matter that would be required would become in tension with other observational evidence given this alternative theory of gravity. That's what the paper says, at least, right? And so this is why the authors from the bullet cluster paper conclude that the bullet cluster provides empirical proof for the existence of dark matter, because they've excluded all alternative explanations. And so in and of itself, I think what the reasoning in the bullet cluster paper already shows is this is a clear reliance on eliminative inferences, right? There's like a list of possible alternative explanations, and then different ones are excluded based on additional evidence. But I think what's interesting is that this reliance is sort of, or what I sort of am proposing is that this reliance on eliminative inferences is an essential feature of astrophysical dark matter research. And the reason is that I think in sort of any individual inferences from a phenomenon to the presence of dark matter, right, there's only gravitational access. But so for a single phenomenon like the bullet cluster, there has to be a reliance on eliminative inference, because you only have sort of one way of accessing the phenomenon that you're interested in. Now, what is the nature of these eliminative inferences? These are not, I think, sort of your cartoon version of identify genuinely independent hypotheses and then eliminate them one by directly comparing them to the evidence. Instead, I think what Shannon Abelson has described as local eliminative reasoning, it's a real tongue twister if you talk fast like me, local eliminative reasoning is a much more accurate representation of the scientific work. And what is local eliminative reasoning? She describes local eliminative reasoning as being model-based. The goal of the eliminative inference, this is going to be tough the entire talk through. The goal of the eliminative inference is to determine which model components should be added to a already established web of models and established evidence. So any eliminative inference is going to happen against a background of models and evidence. And there's always going to be a check in terms of how consistent the proposed model component is with that existing background knowledge. And important, right, that background knowledge can be extremely broad. Abelson gives an example of processual consistency, where she's like, if you're trying to understand, I think the example she uses is about supernova. And she's like, you know, the relevant like background knowledge that you're relying on is not just other supernovae. It's in fact all systems that undergo a similar kind of process, right? So that behave according to the same mechanism. And it doesn't just have to be supernovae, that can be much broader as well. And so we see, I think, this broad spectrum of background knowledge also at work in the bullet cluster. The elimination of alternative explanations was based on a broad a range of background knowledge about the like prevalence of certain structures in the universe, about like pre-existing knowledge of structure formation, of cluster behavior, and so forth, right? And that's where those probabilities came from in the first place. And so I think, so this local eliminative reasoning, I think, is a really insightful way of sort of representing how research in astrophysics and cosmology happens, and especially research into dark matter. So this is basically like the first claim that I wanted to establish, right? That astrophysical dark matter research relies on this eliminative reasoning. But let me now focus on the second claim, which is about this like multi-purpose nature of astrophysical dark matter research. And for this, I'm going to focus on a different, maybe slightly less familiar case, which is that of stellar streams. So as I mentioned in the beginning, right, the behavior of dark matter on subgalactic scales is not yet well understood. And one way scientists have tried to make progress on like understanding the behavior of dark matter on subgalactic scales is by using stellar streams. Stellar streams, what are stellar streams? So tidal stellar streams are astronomical objects that, as the name suggests, they're basically long strings of stars. They originate from a globular cluster or a dwarf galaxy, like the ones you see surrounding the Milky Way on this picture, on this image. And what happens is this cluster or this dwarf galaxy is disrupted, and then the resulting stellar stream is going to orbit the Milky Way roughly on the same orbit as the object from which it originated. So these stellar streams are these like long strings of stars that are moving around the Milky Way. Now, one stellar stream that has garnered quite a bit of attention is GD1. It was first identified in 2006 by Grillmeyer and Dionatos. I'm definitely butchering their name, so apologies for that. But recently, with the help of the Gaia satellite, which also contributed to the current image, a lot more data has become available about the proper motion of the stars in GD1. And interestingly, what has come out of these observations is that it turns out that GD1 is not completely smooth. It's not this very smooth distribution of stars. Instead, its stellar density contains variations. There's 2 or 3 gaps, and there's a spur, which is basically like this bit of stars hooking back along the stream. Now, why is it interesting that GD1 isn't completely smooth? Well, if GD1 was just moving through a smooth dark matter halo, you would expect its substructure to be smooth as well. The stellar stream not being smooth suggests that there's some substructure in the halo of the Milky Way that interacted with the stream. Now, at this point, you may say, like, yeah, of course, there is substructure in the Milky Way halo. Look at all of these dwarf galaxies on the screen, right? And that's definitely true. But it is actually also the case that it is possible, and based on lambda CDM, it is expected that there are some subhalos in the Milky Way dark matter halo that are completely dark, so that there's no sort of star formation or there's no stars or anything like that in those halos. And so what scientists are interested in is trying to figure out what caused these underdensities, these gaps in GD1 or the spur in GD1. And their hope is that some of these causes are encounters with dark subhalos. Because if it turns out that that is the case, then the stellar streams can actually be used to research those dark subhalos, and maybe in that way to further enrich the astrophysical dark matter concept. Sorry, I went a bit too fast. So as a recent review paper stated, right, Baerdemaeker and Prince Willem, this should be 2025, I'm sorry, the date is wrong, says long coherent stellar streams accreted in the Milky Way halo in the Gaia era became our most sensitive antennae for dark matter, right? So like this is the goal, right? Use stellar streams to look at, like to learn more about dark matter. But in order to play that role as detectors for dark matter, right, I think these stellar streams research requires 3 different targets to be modeled at the same time: stellar streams, the dark matter subhalo population, and astrophysical dark matter. And that's what happens in this paper by Baerdemaeker et al. From 2019, which is what I'm going to focus on sort of most for this part. So let's see how they go about their research. So the first target, obviously, that they're interested in is stellar streams. And there's two goals here. First is getting the morphology of the stellar stream right. Obviously, you have to know what you're looking at. And with that in place, and given that they find some gaps in the stream, the next goal is to identify what caused the over and under densities in the stellar stream. So Baerdemaeker et al. Identified two clear gaps in GD1, and at one of those gaps, there's also this spur attached, right? This group of stars that is bent backwards at the gap, right next to the stream. And for this, for the first gap they identify, they say this is associated with the progenitor of GD1. So that's where the initial globular cluster was. But the second gap and the associated spur, that's what they're more interested in. And that's what I'm going to focus on. And I think, again, right, we see this local eliminative reasoning that I described just now at work, because there's three classes of possible explanations that would be consistent with, that are considered, and that they're sort of trying to investigate as explanations for this gap and spur. And for each of them, they're going to evaluate the explanation based on their pre-existing background knowledge, not just of stellar streams, but also of the Milky Way, of galaxies more generally, and so on. So the first is non-impact scenarios. The next is luminous objects perturbing GD1. And the final one is a dark halo substructure. Non-impact scenarios would include things like the progenitor of the stellar stream had a complex substructure, which affected the stream when the progenitor got disrupted. They exclude this based on the fact that the substructure that would be required in the progenitor would have to be super, super complex in order to generate the GD1 features. And so it would be way more complex than the substructure of any of the currently known globular clusters, and so they exclude that. They also exclude a chaotic gravitational potential based on the fact that some of the features of GD1 are extremely well localized. So those two are excluded. That leaves impact scenarios as possible explanation. One would be GD1 was impacted by a luminous object like one of the approximately 200 Milky Way satellite, one of the approximately 50 dwarf galaxies or 150 globular star clusters, so 200 in total, that are orbiting the Milky Way. Again, Baerdemaeker et al. Are able to locate them in 60 phase space, try to figure out their orbits. And the possibility of a collision with a luminous object is excluded because none of these luminous satellites would have come close enough. There is a caveat here about not having dynamical orbit data to double check some of these results, but some further observations they would like to get. Another form of luminous perturbation would be that GD1 was perturbed when it crossed the Milky Way disk. This is excluded based on the density of the Milky Way disk. It basically wouldn't be dense enough to cause the perturbation. Maybe there was a giant molecular cloud, however, in the Milky Way disk causing the perturbation. They don't consider this highly likely because of their background, because of the available knowledge about molecular clouds. Again, the molecular cloud would have to be very, very dense. And they're like, it's possible, but it's not very likely. So finally, they're led to consider dark perturbers. So a perturber that is almost entirely made out of dark matter. One option is a low luminosity perturber, which would be a subhalo which contains some baryonic matter. But this kind of perturber would have to be hiding in the plane of the Milky Way because otherwise it would have been detected already. And so again, they're like, maybe more survey data is needed to fully exclude this, but it doesn't seem like they're considering highly likely. Another option is a primordial black hole. Problem is that there are, from other observations, strong limitations on primordial black holes as contributing to the dark matter budget. So this is again excluded. And finally, there is the possible encounter with a dark subhalo. I'm skipping a lot of detail here, but the authors conclude that within the boundaries of lambda CDM, it is broadly to be expected that GD1 would have encountered a dark matter subhalo on its journey through the Milky Way halo. And such an encounter could have caused the gap with the spur in GD1. The way they go about this is by modeling such an impact scenario through simulations for different properties of whatever it is that perturb the stellar stream. And they then look for the range of possible scenarios that lead to the observed spur and gap. And so it's possible that a dark perturber could have caused the gap and spur in GD1. And so since all of the other explanations are more or less excluded, though there are some caveats, right? They believe that, in fact, we can't use GD1 as a dark matter subhalo detector. It's sort of a proof of principle that these stellar streams can be used as such, right? Here again, right, let me stress, right, there's this clear, I hope that I've sort of hammered it home enough that there's this clear reliance on this local eliminative induction. And that this again is sort of essential, right? Because they can't really do an electromagnetic follow-up observations to find the like GD1 perturber. There is some discussion of maybe using weak gravitational lensing, but even in that case, right, the weak gravitational lensing observations themselves would have to exclude all other possible explanations in order to conclude that they found the same subhalo, right? So if it really is the case that a dark perturber has caused the spur and gap in GD1, so if the eliminative inference holds, this means that stellar stream observations can provide evidence for the existence of dark matter subhalos. And this is what Baerdemaeker et al. Conclude their paper with. They write, further study of the GD1 gap and spur feature may provide the first opportunity to follow up an individual halo substructure. But most excitingly, these features demonstrate that cold stellar streams are extremely fine-tuned detectors, sensitive at a level that was only hoped for beforehand. In addition to GD1, there are over 40 known streams in the Milky Way halo. In the era of Gaia, we now have both the incentive and the resources to study them all in detail. With a full network of streams, we could learn not only about individual halo substructures, but about the population as a whole. So GD1 is clearly being used to also investigate the second set of targets, which is the dark matter subhalo population of the Milky Way. And what's really at stake, right? What they're really raising here as a possibility is using stellar streams to identify individual dark matter halos, but also to actually create a census of dark matter subhalos, to really investigate the entire population of dark matter subhalos. And having such a census could have important implications for astrophysical dark matter, right? Because it could give a better handle on some of the small-scale challenges to lambda CDM that I mentioned before. And so, right, so with this census in hand, there is this third target that stellar streams are used to constrain, and that's astrophysical dark matter. That's the boundaries to the space of possibilities for fundamental dark matter, right? And so this is where this distinction between the two dark matter concepts and how they bear on the space of possibilities for dark matter, I think really comes out, epistemically speaking, right? Because astrophysical dark matter constrains the space of possibilities for fundamental dark matter. And so improving the astrophysical dark matter concept amounts to building up these tighter constraints on that space of possibilities. So for instance, in the current case, it turns out that not all fundamental dark matter candidates would lead to the same substructure in the Milky Way halo. So if you better understand the halo substructure, that means you can actually sort of eliminate some of these dark matter candidates from your space of possibilities. So this is like the third target, right? And so here's a quote from a second group of scientists in a different paper on GD1, which is the evidence for CDM substructures thus obtained can be used to constrain any particle dark matter that leads to a substantial suppression of the dark matter subhalo mass function on subdwarf scales. And so one example is that they derive stringent constraints on the mass of warm dark matter relics, which had separate issues, but yeah. So that's sort of an overview of the stellar stream case. And in my reconstruction, what I've tried to show is that this detection of astrophysical dark matter with stellar streams, first, it depends on this local eliminative reasoning. But also, I've tried to show that these streams are actually used to constrain 3 different targets, right? So let me briefly say something more about the fact that stellar stream research is multi-purpose, right? So stellar streams are used to constrain stellar streams themselves, dark matter subhalos, be it identifying an individual halo, constraining the population of subhalos, as well as astrophysical dark matter. And so ultimately, right, the scientists are trying to map out this population of dark matter subhalos in order to better understand dark matter. But that mapping, understanding dark matter depends on the success of the mapping exercise. And the mapping exercise is only possible insofar as the authors can accurately understand and model the stellar stream substructures and the various impact scenarios that give rise to the stellar stream substructures. So the exploring of the dark subhalo population depends on the success of the stellar stream research itself. If they don't get the morphology of GD1 right, the identification of dark subhalos will fail as well. And so the stellar stream reconstruction provides the background assumptions that are necessary for research in the dark subhalo populations. Of course, the fact that experiments and observations depend on theory is not surprising, right? This point is sort of as old as philosophy of science almost. We need theories of detectors in order to be able to use the detectors to investigate a new target system. But extending that point to the current case, you could argue, right, that the stellar streams serve as detectors, basically. So astrophysicists need a detailed model of their detector and the kinds of signals it produces to be able to use it for the research in dark matter subhalos. But I think what's sort of interesting, right, is that it's the same collection of observations that is serving multiple purposes. It's both used to construct a model of the detector and to construct a model of the target, right? And so the same set of observations is developing the theory of the detector and serves to identify new phenomena with that detector at the same time. And that's sort of what I mean when I say this research is multi-purpose. It's that same set of observations that's doing all of the work. And that also means, right, that making progress on astrophysical dark matter requires making progress on a whole host of targets, not just stellar streams, but also giant molecular clouds, primordial black holes, Milky Way satellite galaxies, globular clusters, and so on. And so this is kind of a happy side effect almost, but it's a side effect that's sort of built into the nature of the research. Is that astrophysical dark matter research leads to progress on more than the dark matter problem alone, right? And this is the second claim that I wanted to establish, right? That doing astrophysical dark matter research, in a way, you are almost more guaranteed success. Like you're almost always guaranteed some form of success because even if you don't make progress on the astrophysical dark matter question, right? Because even if scientists weren't able to identify a dark subhalo, they would have learned a lot about stellar streams anyway, or about other substructure in the Milky Way halo, right? Or about giant molecular clouds. And so this is what I mean when I say that the astrophysical dark matter research can contribute to progress on more than the dark matter problem alone, and also that these success conditions are broader than is usually recognized. So far I've been very optimistic about astrophysical dark matter research, but there are some clouds on the horizon, and this is the final piece that I want to talk about. Am I still good for time? That's the final section. So yeah. I hear nothing, so I'm going to assume yes. Okay. So there's some limitations to be reckoned, and that's what I want to end with in the final substantive part. So the first issue I want to highlight is that the identification of individual dark subhalos, or constraining the subhalo population as a whole, is really dependent on this adequacy of your initial eliminative inference about the substructure of the stellar stream. And setting that inference up comes with serious challenges. Here's a paper by a different research group, De Boer et al. And these authors re-examine GD1, and there's a couple of points at which they deviate from Baerdemaeker et al. First of all, they disagree on the stellar stream phenomenology that needs explaining. They actually don't think the spur is associated with the gap that Baerdemaeker et al. think it's associated with. They think it's associated with a different gap. So they characterize the morphology differently. And they also focus on an additional underdensity that Baerdemaeker et al. Identify but don't really discuss, and they elaborate that underdensity a lot more. And so you might be wondering, wait, how can they disagree on what it looks like? And it's just because identification of members of a stream and separating them out from stars in the Milky Way disk is extremely difficult, And so perhaps unsurprisingly, right, since these people reconstruct the morphology of GD1 differently, the elimination of hypotheses for the spur feature is going to be different as well. And they actually think that it's plausible that the spur was due to an encounter with one of the luminous satellites of the Milky Way, rather than some dark substructure. And so this again shows that the success in research on dark subhalos depends on the success in stellar stream research in the first place. In addition, right, the morphology of GD1 isn't the only point of contention. There's some scientists that use a different method that Baerdemaeker et al. Do to do stellar stream research. Instead of focusing on identifying single perturbers that are responsible for a large underdensity, right? Because Baerdemaeker et al. Basically assume that like the spur and gap are caused by a single perturbation event. These authors actually assume that the substructure in stellar streams can be due to encounters with multiple overlapping halos. And so they try to model these overlapping effects of interactions with multiple halos, and they try to use computer simulations to then constrain the subhalo population as a whole. But of course, even in this approach, right, they still have to make sure that they've excluded encounters with luminous halos and so on, like Baerdemaeker did, in order to be able to get these constraints on populations as a whole. So these are just like two examples of like how this research can change and how this research can be differently approached. But there are also some more general, in principle, challenges that I'm going to briefly introduce and gesture at a reply. So first challenge is that one might be concerned that the success of this local eliminative reasoning relies on the availability of sufficient empirical data. And one might say, well, do we really have enough data in cosmology and astrophysics? This is sort of a version of a sparseness of data issue that Jacquard hints at in 2020. Like Jacquard, I believe that scientists have many ways around the sparseness of data concerns, including by computer simulations, but also many other ways. So like her, I don't think that the sparseness of data issue should be overstated or considered like a principal shortcoming of astrophysics and cosmology. More concerning is a recent paper by Smink and Gallagher, who introduce a difficulty called what they call the problem of uncomputed alternatives. What this refers to is the fact that scientists can't always simulate all possible scenarios that they're interested in due to computational costs. But the problem is that the fact that they're not computing all possible scenarios may introduce unwarranted selection effects or biases in the research. Right? Because if you're not considering all possible scenarios because they're too difficult to compute, then you might actually not know if you're allowed to exclude them or not. And this is something that Baerdemaeker et al. Recognize in their paper. They mention that they would like to create a fully self-gravitating model of the stellar stream, but they don't have the computational power for it. And so this is something that is slightly more concerning, I agree. But I also believe that this is something that can be actively kept track of, and that doesn't necessarily imply that astrophysical dark matter research is sort of doomed or worse off than other kinds of dark matter research. But the most concerning thing, I think, actually comes from the following fact. Most of our knowledge of the structure of a galactic halo comes from observations of the Milky Way and the local group. But the Milky Way is, according to what I've been told by some scientists in Stockholm at least, is an atypical galaxy according to lambda CDM. Basically, it's a very small fraction of galaxies predicted by simulations look like the Milky Way. There's some possible explanations for this, including the Milky Way's formation history or other things, I don't know. But like there's some sort of like explanations that scientists are willing to consider. But evidently, right, getting the typicality of the Milky Way data right is incredibly important for trying to make generalizing claims about the substructure of galaxies for the entire universe, right? Or the substructure of dark matter halos for the entire universe. But so I think generally the atypicality of the Milky Way is a concern. But note that this final difficulty actually does fit well with this idea of local eliminative reasoning that I've adopted from Abelson, right? Because ultimately, what this difficulty points out is that there may be a gap in our background knowledge that needs to be fixed before we can make progress on the research, right? And this idea of local eliminative reasoning can allow you to identify where the important gaps are located. So let me conclude. I've tried to argue for three things. Here they are again. So astrophysical dark matter research essentially relies on what Abelson calls local eliminative reasoning. Astrophysical research, dark matter research, tends to be multi-purpose, which means that it can contribute to progress on more than the dark matter problem alone. And this also means that the success conditions of astrophysical dark matter research are broader than usually recognized, though I have mentioned some important limitations. Thank you. And here are some references.